Hello everyone, I am Yi-Chiao from Nagano University, Japan. Today I would like to introduce our work, a cyclic post-filtering approach to mismatch refinement of neural vocoder for text-to-speech system. This is my outline. First, I will talk about our motivation to build a post-filter for TTS system. Secondly, I will discuss the challenges of building the post-filter. Thirdly, I will introduce our proposed framework. Last, I will give a conclusion. As we know, to develop an advanced TTS system from scratch is expensive. There are a lot of time and resource-consuming requirements, such as label data with alignment information and a very deep neural network. Therefore, we propose a post-filtering framework for existing or low-cost TTS systems. Since the proposed framework is generalized for arbitrary TTS system, and the label data with alignment information are not required, the proposed method is more economical. However, there are two main challenges of building a neural post-filter. First, if we directly take a neural vocoder as the post-filter, the vocoder will suffer from acoustic mismatch. Specifically, the input of a vocoder are acoustic features, and the output is speech waveform. In the training stage, the vocoder is usually trained with paired nature acoustic feature and speech waveform. However, in the testing stage, the input are the synthetic features extracted from TTS speech. The mismatch between training and testing usually causes significant quality degradation. Even if we directly train the neural vocoder using the synthetic features and the nature waveform, the temporal mismatch between them still causes significant quality degradation. Here is an example. We can find that the temporal structure of natural and synthetic spectra are slightly different, and it will cause a serious mismatch problem, especially for autoregressive models. To summarize, the training feature should have matched temporal structure with the natural speech and a similar acoustic characteristic with the testing features. Therefore, in the training stage, we convert the acoustic characteristic of nature feature while maintaining the same temporal structures. In the testing stage, we also convert the acoustic characteristic of synthetic features to fit that of the training features. Specifically, the proposed post-filtering framework includes feature conversion and the speech generation modules. In the training stage, a frame-based spectral conversion model is first trained with nature and synthetic features. Then the nature features are converted by the conversion model for training the vocoder in the speech generation module. In the testing stage, the vocoder generates the enhanced speech based on the converted synthetic features. For the spectral conversion, a cycle VC technique is adopted. A general VC framework includes only a source-to-target conversion model. However, the cycle VC framework has an extra target-to-source conversion model to take advantage of cycle consistent for improving the conversion performance. In the proposed cycle VC framework for post-filtering, we take the synthetic feature as the source and the nature feature as the target. Specifically, the framework includes an enhanced path to convert the synthetic feature to nature feature, and a pseudo VC path to cyclically convert the nature features. Since the cycle VC model is frame-based, the temporal structure are still maintained after the spectral conversion. That is, the temporal structure of the pseudo VC features and the nature speech are matched, while the acoustic characteristic of the pseudo VC features are similar to the enhanced features. As a result, training the neural vocoder using the pseudo VC features avoids the temporal mismatch problem. In the testing stage, the synthetic features are first enhanced by the source-to-target conversion model, and then the vocoder generates the enhanced speech. Since the acoustic characteristic of the enhanced speech features are similar to the pseudo VC features, the acoustic mismatch between the training and testing input is reduced. Here is an example. According to the nature and the synthetic spectra, we can find the different temporal structure, such as the format locations. However, after the cyclic conversion, the pseudo-VC spectrum still keeps the same temporal structures. Moreover, the pseudo-VC and the enhanced spectra have similar acoustic characteristics, such as both of them suffer the over-smoothing effect. If we plot the power spectral density of a short segment, we can find that the nature and synthetic spectra are very different. However, after the conversion, the pseudo-VC and the enhanced spectra are much similar. For the experiment, an internal Japanese corpus was adopted, and the corpus included a female and a male speakers. Each speaker had 800 utterances for training and 100 utterances for testing. Both the TTS system and the proposed framework were trained with the limited 800 utterances. HNN-based and DNN-based low-cost TTS systems was adopted. Moreover, WaveNet was adopted as the neural vocoder. To show the effectiveness of the cycle-VC module, we plot the relationship among nature, pseudo-VC, synthetic, and enhanced features on a NCD plane. Each distance between 2 points on the plane represents their NCD. According to the figures, we can find that the NCD of nature and synthetic feature is the highest, and the high MCD implies the large spectral difference. However, after conversion, the NCD of pseudo-VC and enhanced features becomes much lower, and the lower NCD means the more similar spectra. Furthermore, we also conducted a preference test to evaluate the speech quality of the proposed neural pulse filter compared with the pulse filters suffering from the acoustic mismatch and the temporal mismatch. According to the result, we can find that the proposed method greatly eases the mismatch problems. Here are some demos. First, I play the sound of the proposed method based on the DNN TTS.
泥棒でも入ったかと一瞬僕は思った。
Secondly, I play the result suffering the acoustic mismatch.
泥棒でも入ったかと一瞬僕は思った。
Then I play the proposed method again.
泥棒でも入ったかと一瞬僕は思った。
Last, I play the result suffering the temporal mismatch.
泥棒でも入ったかと一瞬僕は思った。
We can find that the proposed method achieves higher speech quality. We also conducted MOS tests to evaluate the performance improvement of the proposed pulse filter compared with the unprocessed TTS generated speech. The results show that the proposed method improves arbitrary low-cost TTS systems. There are some demos. First, I play the WaveNet with nature features, and it is the upper bound.
泥棒でも入ったかと一瞬僕は思った。
Secondly, I play the DNN TTS result,
泥棒でも入ったかと一瞬僕は思った。
and the post-filtering result for the DNN TTS.
泥棒でも入ったかと一瞬僕は思った。
Thirdly, I play the HNN TTS result,
泥棒でも入ったかと一瞬僕は思った。
and the post-filtering result for the HNN TTS.
泥棒でも入ったかと一瞬僕は思った。
We can find that the improvements are significant. In conclusion, this paper shows the harmful effect of the acoustic and temporal mismatch. Even the TTS system uses the prior alignment information, it still causes the temporal mismatch problem. Therefore, we adopt the cycle-VC framework to generate the temporal matched pseudo-VC feature for training the neural vocoder and acoustic similar enhanced features for positive filtering. Furthermore, the proposed post-filtering framework is generalized for arbitrary TTS system and neural vocoders. More information can be found on our demo page. Thanks for your attention.